Welcome to Lecture 4 on the topic of yield mapping. This lecture is part of the subject Future Farming Technologies, which is a component of the Bachelor of Agriculture and Technology, offered at both North Melbourne Institute of TAFE and Melbourne Polytechnic. Please visit our website www.nmit.edu.au for further information on this subject and other courses that we offer. I would like to take this opportunity to acknowledge Sally Heaps for some of the resources and information that has been used in this lecture. The image on the screen shows a yield map of soybeans. The topics covered in Lecture 4 are part of Student Learning Objective number 2, where you will examine and evaluate different technologies such as GPS systems and sensing. So, what is yield data and yield mapping? Well, yield data is data that is collected at the time of harvest. It is an important measurement for many enterprises. The data is captured usually by monitors on tractor. They capture relevant information on the harvest. That can include the weight, the amount, and/or the quality of the crop. The data can then be exported into a spreadsheet, usually as a text file that has a TXT format at the end of the file. The image on the screen shows you what the raw data from a typical yield monitor might look like. Each number refers to the quantity of the yield. Raw data can contain gaps, as you can see from the image on the screen. Data can be processed and used in many ways. Here is an example of 4 years' worth of yield data that has been superimposed. The result of this data manipulation and processing is that you are able to obtain both temporal and spatial information at one time. On the slide you will see an interpreted map of the yield data. This is the format we commonly see in agriculture for the yield data. The dark areas in black are associated with high yield frequencies, while the lighter colours in white are associated with very low yield frequency. We stated in an earlier slide that sometimes information is missing. When it is the characterizing information such as the yield or rainfall or elevation data that is missing, you need to do something with the image. The nature of the images mean that you can't just leave them as they are, like blank, because this is misleading. So in GIS we tend to fall on a technique called spatial interpolation. There are many methods for this, but they all calculate the values of data which may be missing. Most commonly, they calculate the values of data taking information from the surrounding data. This, of course, sets presumptions. So let us have a look at some of the spatial interpolation techniques that can be used. There is the local. This is based on a mathematical function that is applied to surrounding points, and it is based on some local sample point information. Within ArcGIS, which is a commonly used software, there is an inverse distance weighted, or IDW, which is based on a local technique. There is also a natural neighbour technique. That is, if your yield is 20 tonnes per hectare and the missing point next to that, you would then assign 20 tonnes per hectare to it. It assumes that the spatial variation does not change greatly over small distances. There is also a global interpolation technique. This is where you use a mathematical function to calculate from the sample units and apply across the whole data set. You could almost think of this as a type of mean. Therefore, if you were missing a yield at one point, you could say, because the mean was 20 tonnes per hectare, I will put that value in. ArcGIS, for example, uses the spleen and the trend options for global units of data. There is a third category, which is an exacting category, or exact. This is created, This creates surface passes through the sample points. Hessian polymers are a type of exact interpolation, as the value of the points near the sample point take the same value. Another example of this is TIN, or Triangulated Irregular Network. This is often used in digital elevation models. And finally, the last one I'd like to introduce to you is called kriging. This is perhaps the most commonly used form of interpolation with respect to agriculture and yield maps. The basis of this technique is the rate at which the variance between points changes over space. There's a variogram, which is a type of maths, is used to show the average distance between the values at points that change with the distance between the points. So what do all these spatial interpolation techniques actually mean for you as the person who may be using this information? Well, it means that where data is missing, you may get a slightly different story or impression of how your yield is varying, depending on which technique is to be used. On the screen, you see an area. This is 4 different types of interpolation techniques have been used. IDW, the spleen technique, the Hessian technique, and C. kriging. As you can see, just having a snapshot at these images, that each one of these shows you slightly different yield maps. Therefore, you may take home different messages, and you may conduct different management techniques depending on which one you had the information for. Therefore, it is important that you understand some of the assumptions and the problems that are associated, as well as the advantages, with each of these different techniques. The following illustration shows both the interpolated data, that is in the light green to dark green coloration on the slide, and the actual data points. They're shown as diamond with the figures. If you study this image, and you may want to pause the presentation here to do so, you can see how the techniques have filled in the spaces between the actual data points. The location of the data points are actually where the data was obtained. You can also see that the 3 different techniques compared, IDW with spleen and natural neighbours, all show a slightly different yield mapping interpretations. Let us reflect on what we have learnt in this lecture. You should be able to give examples of what data is used for yield mapping, how yield maps are created. You should be able to describe the process of interpreted data and spatial interpolation. You should now be able to understand some of the advantages and disadvantages of spatial interpolation. And I'd like you to take a few moments to think about how spatial interpolation may impact on agricultural management decisions. This brings us to the end of Lecture 4.